Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel. And today second day of our Eid here, and once I'm not having any guests, so I thought I must prepare the second video that I promised you last time. So over here you can see that the first order ordinary differential equation series where we are just engaged with, and in this video we are going to learn how to reduce a non-homogeneous first order differential equation into a homogeneous one. So we are basically having two cases here. So in this video we are going to discuss the first case. Okay, we are going to discuss the first case. So what is that case and what kind of non-homogeneous equation is there in case number one? So let's see, like in general, if I just try to write that I'm having a non-homogeneous equation here. For instance, in general, it is a1x plus b1y plus some constant c1 dx plus a2x plus b2y plus c2 into dy equals to 0. You can see that this is the first order ordinary differential equation. So let me just try to write this equation in terms of dy upon dx. I've just shifted this part on the other side of your equals to sign. Okay, so now I'm going to shift this coefficient or this part of the function over here and this differential over here. So it looks something like this: dy by dx equals to minus either you write this negative sign with the numerator or with the denominator. It's not going to make any difference. Okay, so that's it. So over here, once when you examine that, if the ratio of the coefficients of x in both numerators and denominators, if this ratio is not equal to the ratio of the coefficients of y in both numerator and denominator, in case number one, if these two ratios, if they are not equal, then in that case what you are going to do, you are going to replace, in this case you're going to replace your x by your capital X plus h. These notations I'm using, you can use any notation you want, but conventionally we use these two notations. In the place of our x and at the place of our y, we are going to put capital Y plus some small k. Okay, these are the two substitutions that we are going to make, and after that we are going to have some this non-homogeneous equation will be reduced or will be transformed into a homogeneous equation, and then we are going to perform the same transformation of that homogeneous equation into an equation of separating variables, and after that we are going to perform the same strategy we used in the first video of this series. You can see the links in the description box. So what we are going to do, we are simply going to substitute these values in the place of our xy in this entire equation. Okay, and after that what we are going to do, I'm not going to move on with the oral work. Now let's move on to let's look to the example, and then we just try to understand this entire strategy of case one more deeply. So let's see the example here. Okay, so this is the example that I've managed, and you can perform the homogeneous testing that we learned in the previous video. You can also find its link in the description box. So I'm not going to check the testing work. I'm not going to perform testing in this example. It is already done in the previous discussion. So let's move on, and I'm just going to tell you directly that this function dy by dx, this function f of xy, this is actually your f of xy, right? This is not homogeneous at all. Okay, So this is a non-homogeneous function. We have to reduce it into homogeneous form. So let us now compare this equation with this general form. Okay, let me just close it in a box for our a's. Something like this. Okay, so once when you just try to compare this general form with this equation, you can see this is your a1. Okay, a1 is your 2, your b1 is your -1, c1 is your 5, a2 is your 2, b2 is your -1, c2 is your -4. It's something like that. But let us try to check, are these ratios equal or not? So you can see that my a1 is 2, my b1 is -1, my c1 is 5, okay, my a2 is 2, my b2 is also 2, alright, and my c2 is -4. I'm sorry, my b2 is -1. I'm sorry for that. Oh, I just did a little bit, it's a little mistake, but it's going to present a gigantic consequence. So I'm happy that I've just identified here. This is actually your b1, this is your a1, because you see first we are having y here and then we are having x. So if you just try to compare with this general equation, okay, so here my x coefficient is a1 and over here it's -1. So a1 is -1 here, so I just did a mistake here. So this is your -1 and b1 is your 2 over here. Okay, let me rectify this thing. This is your 2, okay, and this is your -1, so I just cut it gently and this is going to be your -1. Alright, so let us now try to check that a1 upon a2 is your -1 upon 2, which is actually your -1/2, and your b1 upon b2. b1 is your 2 and b2 is your -1, so this is giving me -2. So you can see that this ratio and this ratio are giving me two different answers. So this thing yields that my a1 upon a2 is not equals to b1 upon b2. So now I'm going to replace my x, small x, with capital X plus h, and a small y with capital Y plus k. Okay, and you can see over here that if I just name these equations as equation 1 and equation 2, and if I just try to differentiate both these equations with respect to our original variables, alright, so what exactly they are going to give me. So if I just talk about my first equation and I just try to differentiate both sides with respect to my x, original variable small x, okay, this is going to give me y, and over here I'm going, and this is some constant number, okay, so it is giving me 1, and this is going to give me dx by d small x plus dh upon dx. So this thing is definitely 0, so I'm having just 1 equals to dx upon d of small x. So now I'm going to shift this thing over here. So d of small x equals to d of capital X. So I'm going to replace my d of small x with d of capital X, okay? And in the same way, I'm going to differentiate both sides of my equation 2 with the original variable small y. So going to perform the same work just like this, and in this way, once when I perform the derivative, let me just do the work here. If I just tell the thing orally, I personally don't get satisfied that much. So that's what we are going to do here, okay? And afterwards we are going to perform the same work. So in this way, now I'm going to be a bit direct. This is going to give me dy is equals to d of capital Y. So I'm going to replace d of small y with d of capital Y and d of small x with d of capital X, alright? and at the place of our small y and small x, we're going to substitute these values. Alright, so let's do it on the next page. Okay, so that's how it looks like. Alright, now let us just try to simplify it. You can see that it seems to be, it comes out to be something this. On it's 2 times x plus 2 times small h minus y minus k minus 4. Okay. Now let us write down here the big variables and the on one side together and the constant terms together. Okay, so that's what we are getting. Now what we are going to do in order to reduce this equation non-homogeneous into a homogeneous form, what we are going to do, we are going to pick up this part and this part forming two linear equations and then try to simplify them and try to solve them simultaneously to get the value of your h and k. Okay, that's what the thing that we are going to do. So you can see that this is your equation number 1. Okay, and this is your equation number 2. How about if you just write it in English numbers? Because previously I've given 1 and 2 the equation x plus h and y plus k in Roman form, so that's fine. Now what we are going to do, how about if I just decide, I've just decided to eliminate my h variable. So for that purpose I'm going to make my coefficients common, obviously. So this is just a basic elimination process, so I'm not going to elaborate that much. Okay, so on multiplying equation number 1 entirely with your 2, and then adding it with your second equation, so we come to know that our small k value is your -2. Alright, that's it. Now you can substitute this answer k either in 1 or in 2, that's your choice, and we are going to get the value for h, obviously. Okay, so I can do it over here. I've selected here equation number 2, and 2h minus k, the place of my k I just put my -2, minus 4 equals to 0. So it gives me something like this. Okay, so h is coming this, therefore h is your 1. Alright, so h is your 1, k is your -2. So once when you substitute these two values over here, they will definitely get 0. This part and this part will get 0 once when you substitute your h and k. Okay, so no need to show that work, it is obvious. So once when you substitute k and h values over here, these two parts will get vanished and just this is left. Okay, so once when you do that, I'm now having just this. so left. Okay, and this is indeed your homogeneous form. Okay, now this function is your homogeneous function. You can check it through the process of your homogeneous testing, which is discussed in the previous video. The link is, once again I repeat, as if it is in the description box. You can see over there, and you can learn how to test the function homogeneity. So once when we perform that testing work, we come to know that now this function is indeed a homogeneous function. Now we are going to solve this homogeneous first order ordinary differential equation by transforming it into a separable equation, and then performing conventional integral strategies. Okay, so what we have to do in order to transform this homogeneous function into a separable equation, so we are going to substitute our y by our small v of nx. Okay, just like we did in the previous video. Okay, so that's what we are going to do, and you can see that once when you differentiate both sides with respect to your x, then we are going to get dy by dx. Okay, so once when we differentiate both sides with our first variable, okay, so you can perform, you are going to use your u into v formula of your derivatives. So at the place of our dy by dx, we are going to use this, and at the place of our y, we are going to use this. Alright, so this is the equation here, and let us now try to transform it. Alright, so I hope now the concept is getting clear in your mind. Definitely it is going to be, I'm sure. Okay. So you can see in the numerator and in the denominator we are having x common. Just take it out. In the denominator we are having, I'm sorry, it is simply vx. In the denominator again we are having our x here, so just 2 minus v is common. Alright, I hope I'm fine. I'm doing quite fine here. So it is now x and x get cancelled. What we are having is 2v minus 1 and 2 minus v here. Okay, so now we are going to shift our v over here. So x dv upon d of x is equal to 2v minus 1 upon 2 minus v minus v. Then we perform a good LCM work. And 2 minus v. Alright, so it is 2v minus 1 minus 2v plus v square upon 2 minus v. Alright, this and this gets cancelled. We are having v square minus 1. We are having v square minus 1 in the numerator and 2 minus v in the denominator. Okay. We are going to shift this function on this side. Now going to perform definitely a separating variable format. So once when we are going to perform that, what we are going to do, we are simply going to put our x variables and the differential corresponding on one side, and v variables and the corresponding differential on the other side. So what we are going to do, we just shift this function over here along with the dv, and x and dx will shift it over here. Okay. So it looks something like this. Sorry, dv, and this x will go on the other side and becomes 1 upon x times dx. Okay, so that's it. So this is definitely there. Once when we perform integrals at both sides, we are having stuff like this. So the right hand side integral is quite easy to be evaluated. We're simply going to get the log of x here plus some constant. But over here, we are going to perform some exhaustive integration. We can use here by parts. We can use here partial fractions. So how about if we just do it like this? I'm just solving this integral first, okay? I'm not touching this side at all. I'm just trying to figure out this part first. So this can be written in this way, the denominator. It can therefore be handled. It's now definitely the first type of the partial fraction. dv. Alright, this is it. We have to find the value of our a and b here. Alright, so let me just name this equation as my equation star. Okay, I call it star. I'm going to resume the star equation later on because first I have to solve this thing. So I'm just focusing over here. So once when we just try to solve this integral by means of partial fraction of type 1, you can also see the type 1 partial fraction strategies if you want to learn it. And I will put its link also in the description box for your A's, okay? So alright, so let us focus just on the integrand. Let us focus just on the integrand. Okay, so now we will apply LCM over here. It looks something like this. Okay, so this and this will get cancelled, and we are now having simply this thing left. Oh, I'm sorry, it's negative 1. So as in this type of partial fraction, we are just dealing the linear factors. So whenever we are having linear factors along with the unknown variable a and b, or unknown constants and e and b, then for that purpose we simply put the values of our v by equating the corresponding linear factors to 0 like this, and this is going to give me the two values of my v that will help me in getting the values of my a and b. Okay, so one by one I'm going to put my v values 1 and minus 1 in this equation, okay, and that is going to give me the value for my a and b. Okay, so once when I put v equals to 1 here in this equation, for v equals to 1, okay, so b definitely gets vanished, and I'm going to get the value of my a here. So a is therefore half. So the value of a is half here. In the same way, for v equals to minus 1, once again I'm going to put the value of my v in this equation. This time my a is going to get vanished. Okay, and I'm having the value of b as negative 3 by 2. Okay, this is the value of my b, and I'm going to put my value of a and b in this integral and try to simplify it. So it is going to give me 1 upon 2 integral of 1 upon v plus 2 d of v minus 3 upon 2 integral 1 upon v plus 1 d of v. Okay, so we can now directly we can apply the integral. It's going to give me ln of v plus 2, and this is going to give me ln of v plus 1, all right, plus some constant. I'm sorry, it's v minus 1. It's v minus 1. So it's going to give me ln of v minus 1, and this is going to give me ln of v plus 2. Okay, the log of v minus 1, log of v plus 1. So it's like that. So once when I'm going to solve these integrals and this integral in the star, then I'm going to get ln of x equals to half ln v minus 1 minus 3 by 2 ln of v plus 1 plus some constant. So here I am. Alright, so it is going to give me ln of x. And over here at this side, I'm also getting some constant value, and I've just shifted that constant over here. This integral constant was 1 and this integral constant was 2, so I just shifted my 2 here. It's something like that, alright? And once when you subtract two constant numbers, then definitely you're getting some constant answer, and that constant answer can be expressed as log of some constant number. So how about if I just directly write c1 minus c2 equals to ln of some constant number? So I can represent that constant number with my c prime. Okay, so I'm just trying to be a bit direct. So I'm going to replace this thing with my ln of c prime. Okay, over here half is coming common, and I can write this thing in this way. Ln of some constant number. So we are going to use here the basic formulas of our log. Like if you're having log of AB, it is expressed as log of A plus log of B. If you're having log of xn, it can be expressed as n of log of x. And if you're using log of A upon B, it can be expressed as log of A minus log of B. So over here we're going to use we're going to take the reference of these formulas here. So this can be expressed, this side can be expressed with the help of this formula. So it is half of your ln v minus 1 minus ln v plus 1 cube. Okay, and over here I can use this formula that can be expressed as ln of c prime x. Okay, and I can shift this 2 over here on this side, and over here I can apply the log of A upon B. I better use square brackets. Okay, c prime of, I'm sorry, it's capital X, not small x, it's capital X. C prime of my capital X. Alright, so ln of my v minus 1 upon v plus 1 whole cube is equal to, once again I'm going to use the formula of my xn over here. So it can be expressed as c prime x square. I can cancel my this ln and this ln. Alright, so it is v minus 1 upon v plus 1 whole cube is equals to c prime x whole square, and that's it. Now I can shift this side, this denominator over here, it will get multiplied with this thing. So, and one thing more, if I just apply square on both these terms, it becomes x square, and this is going to give me c prime square, and then square on any constant number is once again a constant answer. So I can represent c prime square with my c double prime, another constant number. So I can replace it like this. Okay, but this is just for our a's entirely. Okay, so v plus 1 whole cube can be expressed by means of c prime square x square. So I can also write my v minus 1 is equals to c double prime square multiplied by v plus 1 whole cube. Now we are going to restore our whole work right back. So we know that our v was initially obtained from this relationship. So v is actually y upon x. At the place of our v, we are going to write capital Y upon capital X minus 1 is equals to c double prime x square v upon x plus 1 whole cube. Alright, now let us try to simplify it further. Okay, now taking out this taking out the LCM of this thing. Whole cube. Okay, so you know that your c double prime x square, if I just try to apply my cube on the numerator separately and on the denominator separately, then this and this gets cancelled. It's simply going to have simply x in the denominator, 1x. So this is going to give us a form like this. Okay, this and this then get cancelled further, and now we are having much easier form. So left. Okay, this is it. Now we know that initially when we were in the beginning of this this example, we represented our x with small x with our capital X plus h and a small y with capital Y plus k. So we can represent our capital X as x minus h and capital Y as a small y minus k, and we just calculated and we just solved the value for our h and k, and it was what? It was, let me just see it, yeah, it was h was 1 and k was minus 2 here. So this thing tells me that my x is h minus 1 and my y is small y minus 2, that is y plus 2. Okay, so wherever I'm having my capital X, I will write this. Wherever I'm having my capital Y, I will write this. Okay, so it's going to be y plus 2 minus x minus 1 is equals to c double prime y plus 2 plus x minus 1 whole cube. So on solving, plus 2 plus 1 give me 3 into c double prime x plus y plus 1 whole cube. So this is finally my solution of the non-homogeneous first order ordinary differential equation. Okay, and this was the case 1 of this type, which was this. Okay, now I hope the concept is somewhat clear in your mind after looking this video entirely. So in the next video we're going to discuss the case 2 of the same topic. Alright, so if you find this video helpful, I once again request you to subscribe my channel and hit on the like, hit on the bell icon, and don't forget to write your comment in the comment box below. Take good care of yourself. I'll see you soon in the future. Allah Hafiz.